Okay, good morning. So today we're going to start the topic of Bessel functions, a new chapter in the course. And I should point out that just like in the beginning of the class, we have to go through some introductory topics and some preliminary stuff, um, not only about how Bessel functions arise in the process of solving some partial differential equations, but also once we establish what these functions are, we need to go through some lessons in which we learn some of the most important properties related to Bessel functions, how we manipulate them, how we make computations with them, and more importantly, some important properties of these functions that are related to solving a partial differential equation. So at this point, you should realize, because sometimes students are frustrated by going through a couple of topics without realizing in the beginning what's the connection with solving a PDE. I hope at this point this will be a little bit easier in the sense that um, easier to understand why you need to do this preliminary stuff. Because you should remember how we started the class with Fourier series before we could actually discuss how the separation of variables method works in solving a PDE, a boundary value problem. We really needed to actually understand, what a Fourier series is, some of its important properties, how you obtain the Fourier coefficients, so on and so forth. And then finally, when everything comes into place in a logical manner, you can start talking about solving a PDE involving those functions. So this is going to be the same thing, basically. The first couple of sections will deal with definitions, properties of these functions. And let me state a couple of things about the sections covered. So chapter 9, we're going to go over these sections mentioned here. Notice not all sections are covered. So go by the notes and what I covered during the video lecture. And then when you read the book, feel free to skip the stuff that I don't actually cover in the lecture. Another important remark is there's a handout called Bessel functions, which is available on Blackboard under our course webpage. Make sure you print that out as soon as possible because it summarizes all the stuff you need to know about Bessel functions in order to solve PDEs involving these functions. So it's like a summary of what you need, it's from the book basically, but in a more compact form so that you can have an easy way to refer to it. So make sure you print that out at some point. Okay, so let's review something that we talked about already. This should be familiar territory. If it's not, if it looks like something new, it's probably worthwhile to allocate more time to review the stuff we covered already. So one thing I want to mention first is that the only Sturm-Liouville problem encountered so far in the process of solving partial differential equations was this second order ODE, x double prime plus lambda x equals 0. And remember that depending on the boundary conditions, you end up with infinitely many solutions, also called eigenfunctions, eigenvalues and corresponding eigenfunctions. So for example, you can, let's say you are in the interval, for simplicity again, let's say you are in the interval 0 pi. So the eigenfunctions and eigenvalues were n squared, and the eigenfunctions were either sine of x, sine of 2x, sine of nx, and so on. Or if you have other boundary conditions, you could have a family of cosine functions as the eigenfunctions. And the most important property, in addition to the fact that these should have infinitely many eigenfunctions so that you can come up with a series solution, the main property that allows you to eventually solve the PDE is the so-called orthogonality property. So let me illustrate again how that comes to be. At the end of the problem, as you know already, let's say you have these eigenfunctions, the family of sine functions. toward the end of the problem, you will need at some point to match a function with a series involving these eigenfunctions. So the last part of the problem, so to speak, is figuring out these coefficients a1, a2, an, so that the function on the left side, which is typically an initial condition in the boundary value problem, so that this function can be represented by this series of functions. Now, what is the key property about these functions which allows you for this representation to be possible? Because again, not every family of functions can give you a representation for a given function f of x. So it's not just that you have infinitely many of them to form a series. They need to have an important property that allows you to actually determine a1, a2, an for a given function f of x. And if you go all the way back to the beginning when we study Fourier series, the main properties are the so-called orthogonality. You might remember that on the interval 0 pi, that was one of the homework problems in the beginning. If I take the product of sine n of any two of these functions in this family, sine nx, sine mx, then all of these types of integrals are 0 if these functions are distinct, so if m is not equal to n. And if m is equal to n, the integral is not 0. So in particular, in this case, it was pi over 2. So that is really the key property. Or more specifically, it's the orthogonality property on this interval 0 pi. And why that's the case? Well, remember how we obtain the Fourier coefficients, right? Let's say you fix n and you multiply both sides of this equality by sine of nx. All right, so and then you take the integral on both sides, right? So you have f of x sine of nx on the left, and on the right you have a bunch of products of distinct functions in this family, sine of 2x, sine of nx, all distinct except the one corresponding to n. Sine of nx is sine squared of nx, and then the rest of them again are distinct. So when one takes the integral from 0 to pi in this equality, all of these integrals are 0 except this one. And that allows you, let's do one more step just to refresh the memory. You can pull out an, and that finally allows you to find the Fourier coefficient, which is the ratio of these integrals. You can basically maybe skip writing this down because you already have it in the notes in the beginning. Maybe refer back to the notes in the first part of the class. I just want to refresh your memory with this important property. So again, in the process of solving a boundary value problem via separation of variables, we need to end up with something called an eigenvalue problem. That is an ordinary differential equation that leads to infinitely many solutions. But those infinitely many solutions should have this orthogonality property, namely that on that appropriate interval, which may be different, right, depending on the case, on that interval, the integral of the product of any two distinct ones should be 0. And then if they're the same, the integral should be non-zero. That's also needed because notice when I solve for that coefficient an, that integral, when they're equal, appears at the bottom of the fraction. So why do I say this stuff? Well, because guess what? There are other Sturm-Liouville problems besides this one that come up in the process of boundary value problem solving. And the method still works, but we're going to have different types of functions that still have this orthogonality property, which means you can still pursue the same method. Again, the only difference fundamentally is that we're going to have a different Sturm-Liouville problem with different eigenfunctions. And moreover, I want to mention here at this point that you can have even something more general than just orthogonality in this sense, slightly more general, which is the case when we move on to Bessel functions. We have something called orthogonality with a weight function. So let me illustrate what that means on the second page. And then you'll realize that, sine and cosine are essentially orthogonal functions with a weight function 1. In other words, you can relax this property and have something slightly more general and still have the method working out for you. So let's write down a definition first, and then we're going to illustrate back with sine and cosine maybe, or more generally with unspecified orthogonal functions. So suppose we have a family of functions x1 of x, x2 of little x, xn of little x, and so on. And let's write a definition here. So we say that x1, xn, and so on are orthogonal on the interval 0 c with the weight function let's call it w of x if the integral from 0 to c of w of x, xn of x, xm of x dx is 0 if m is not equal to n, and not equal to 0, let's not specify a number here, if m is equal to n. So in other words, some functions may not be orthogonal by themselves, just like sine x, sine 2x, sine nx, or cosine functions were, but they can be orthogonal with the aid of this extra weight function. And the method still works like a charm. And I'll illustrate immediately what that means, but let me just make it as a remark here that under this definition, you could say that sine x, sine nx, and so on, or the cosine functions, all of these are orthogonal on the interval 0 pi with weight function w of x equals 1. Okay, so when you say the weight function is 1, it means that they are orthogonals by themselves. But they can be orthogonal, like I said, with another weight function, w of x. This extra weight function simply expands the applicability of this method because, as I said, some functions, and this is the case of Bessel functions, as you'll see later, are not orthogonal by themselves, but they are orthogonal with the aid of another weight function. It's w of x equals x, actually, in the case of Bessel functions, but we'll talk about that when the time comes. So let me illustrate, generally speaking, how that method works for a generic eigenvalue problem. And then on the second part of the lecture, we're going to introduce the boundary value problem that leads to what we're going to call a Bessel equation, whose solutions are Bessel functions. So suppose you have a Sturm-Liouville problem. Again, we won't specify it. So suppose you have a Sturm-Liouville problem whose eigenfunctions are x1, x2, xn with which are orthogonal on some interval with a weight function w of x. All right, and just like with any problem to be solved via separation of variables, at some point at the end of the problem, you will end up needing to write a series representation for f of x in terms of these eigenfunctions. Right? So just like you had to do it with, in the case when these were sine functions or cosine functions. So suppose you have a family of functions, x1, x2, up to xn, and so on. And then you need to have this representation at the end, for example, to match an initial condition in a boundary value problem. How do you determine the coefficients? That's the key thing. How do you determine a1, a2, and an, and so on? Well, if you know these are orthogonal on the interval 0c with the weight function w of x, you could simply do like before, fix some index n and multiply both sides by w of x and xn of x. Okay, so you basically simply have to multiply not only by xn, but also carry over that weight function as well. And then you end up with, on the left side, you're going to end up with weight function f of x, xn of x. And same thing here on the right-hand side, a1, w of x, x1 of x, somewhere in the middle, an, w of x, xn squared of x, and so on. And then when we take the integral on the interval 0c, again, all of these integrals are 0. This is x1 of x times xn of x, I forgot, right? Because you multiply by w of x, xn of x everywhere here. So all of these are 0 except this one. And then you can solve for an just like before by pulling it out of the integral. On the top, you're going to have the integral from 0 to c f of x, xn of x dx. And on the bottom, the integral from 0 to c w of x, xn squared of x dx. So this is the recipe essentially of solving any problem via separation of variables, provided the Sturm-Liouville problem gives you orthogonal functions, maybe with some weight function w of x. So far, the weight function was 1, right? I mean, if xn of x was sine of nx or cosine of nx, then you needed to put 1 here because these were 0 with w of x equals 1. But like I said, in some other cases, you need a different function, which will be the case in the context of Bessel functions. So that is going to be the overall idea. Again, to anticipate, in the case of Bessel functions, this w of x will be actually equal to x. So that's the overall difference between Fourier series in terms of sine and cosine and Fourier series involving Bessel functions. So on the second part of today's lecture, let's illustrate the typical PDE that leads to an equation whose solution is given by the Bessel functions. And I think that'll be enough for today. So stay tuned for the second part.